Okay, let's look at another kind of multiple sample design. In this case, we have two independent samples. So you might have an observational design where you have two separate groups of individuals that you're comparing, or you might be doing an experimental design with parallel samples, such as a traditional randomized controlled trial. So, typically you will have two samples of individuals, and on these two samples of individuals you will have collected data on some continuous variable, and you're interested in how these two sets of independent data, because they have come from two separate samples of individuals, differ to one another. So for example, in the observational case you might have two separate groups, and you're interested in comparing, for example, the strength between these groups. So you measure strength and then you compare this between the two groups. Or, for example, in an experimental context, you start with a single group of individuals, but you randomize these into two separate samples of individuals, and then you have them both complete different interventions, and then compare these two sets of data that you collect. So, typically you end up with data something like this. You'll have two groups of individuals. Now, let me just clarify that the distance between these points on the x-axis, so that is to say the horizontal difference between these 2 points, is just to make it visually a bit clearer. I've applied a little bit of what's called a jitter to the data. This is not because there are different values of x for them. Now, we can think of our general linear model formula as we've introduced previously, where we have some variable y and we want to be able to predict that. And we typically have an intercept, which tells us what the value of y is when x is 0, and we have some slope, which tells us how much does y increase for every unit increase in x. And then, of course, we have our error variable as well. Now, how are we going to do this when we've got two separate groups of individuals and we don't necessarily have values for x? Instead, we have what's called a categorical variable. So, for example, this could be individuals that were randomized to the running intervention and individuals that were randomized to the weights intervention. How do we apply our general linear model to this kind of data? Well, we use something called dummy coding. What we do is we take each of the groups of individuals and we apply a value for x. So, for example, we can say that for our first sample, we'll code x as being equal to 0. And for our second sample, we'll code x as being equal to 1. Now, if you remember, our beta 1, or our slope parameter, tells us how much y increases for a 1 unit increase in x. So, if we code our two groups as 0 and 1, what this will tell us is what the difference is between the means of those two groups. So, our general linear model, when we use this dummy coding for two independent groups, ends up looking like this. We have our our intercept value, which is equal to the mean for the first group, coded as 0. We have some slope value, which is equal to the difference between the two groups. And if we wanted to calculate from our regression model the mean for group 2, we could take our slope and we could add our intercept's value to it as well. Now, this is what typically gets called an independent samples t-test. And again, similarly to the other tests that we've looked at, there is a non-parametric version of this where we can rank our y variable and then apply our regression model to predict the rank value of y, and this is what is often called a Mann-Whitney U-test. So again, we can see that there is equivalence between the regression models and the tests that you would normally come across, or that you can at least see that the tests are all underpinned by the same underlying general linear model. Again, there will be some videos to follow up on this to show you how to do these different analyses for this kind of study design.